Okay. In this week, we start to a new topic in Python programming language. Can you please close the door right now? Introduction to probability. In this week, we should talk about it because in the generative AI or any representation of the neural networks or the machine learning function can transform the probabilistic rate. For example, in the classification, we just create the probability values of each class. Or in generative network, we just only calculate to the joint probability of the image or the signal or something like that. Okay? And so this is important because up to now we have dealt with up to now. Firstly, we generate to x and y. This is the input and the output value, and if we have this data set, and then we can create the decision model or the linear regression model. Okay, or we can just give the x1 and x2 value in here, and we separate to this data into two classes by using the logistic regression or the neural network application. Or in the multi-layer perceptron or the neural network application, we can just think that if we have this kind of data like this one or square, and we can generate the 4 dimension or the 4 area for for this representation. And so this is the MLP application, this is the logistic regression, and this is the linear regression. Okay, either classification or the regression problem involves to target decision boundary, or we can find for this application in machine learning to exact solution. Okay, but for doing this or for this purpose, we just utilize to the training data and we propose a model and we generate the outputs. Okay, either classification or the regression, but in some domain which is the absolute. Okay, absolute, exact. For example, for a given data x1 and x2, we generate to the class 1 or class 2, not a probability of this rate. Okay, either two condition is true, but both cannot be. Okay, and so in order to learn about this data representation, we should train the network, either the logistic regression or linear regression or multi-layer perceptron. We have the supervised or unsupervised learning. In this domain, we can generate the exact solution, but in optimization. Okay, we may have the false results, but the result is false. Okay, and so in order to overcome this problem, or in order to create a chance to create or happen any events in the machine learning, we can use the probability theory. In the probability theory, we cannot say that this is the 1 or 0 or class 1, but class 2. But we can give or produce to what 90% class 1, 10% class 2. Like in real life application, the probability theory is the closest one to what? To decision process in human or the any kind of biological system, especially for the what? The nervous system. Okay? And so we can generate the what? The percentage value. Just simple as that. Okay? But how can we do that? We always we should define the problem in here. The problem is that we have logic values, which means that we have 0 and 1 at the absolute process or the exact solutions. Okay? And so these exact values produce to what? For example, if we have the three kind of data, x1, x2, and x3, we can generate to what? This is the one value, this is the one value, and so we can assign the any variable in here, like this one. And so if this is our variable or the search variable, and then we can say that this is the one, true values, or predicted class. Okay? And so, but in real life, we have the chance or the probability of this to what? Happening this class, C1 or C2 or C3. Okay? So, main problem or main question is that how can we distribute this line which means that in this case this is the line. Okay, this line in order to represent the probability. This is the exact number, but we should condition to what? To area or the chance range. Okay, and so solution can be written like that. Solution is written as in the linear algebra, and we have the numbers, this is the linear algebra, and we have the geometry in here, and so axis or the 3D dimension or the representation gives us these solutions. But in the total domain we have these one values like this one. This line 1 can be interpreted into the what? Area form, like this one. In order to obtain to the what? The chance of the probability in here. For a given x value, if we have the 1, this is equal to the what? The 100%. Okay? This is the exact values. But how can we interpret this one line into the area? Because if we have the probability or if we have the many components in this system, we should change to the what? The one line to the area or n-dimensional forms. Because in optimization problem, we always lose or minimize the energy form. Okay? And so this logic can be interpreted as an area or the energy of a chance. Okay? And so if we have this information, and then maybe we can drive this kind of probabilistic area in here, like this one. Okay? This is the base information or the derivation rule for the probability. Probability and the logic states can be discriminated by using this notion. And so if we have the area or the energy form, we can minimize it. And so if we can minimize it, and we can build a model. But in probability theory, we can split the decision into the area. In order to what? In order to get the chance or the probability or the happening rate of the what? This line. Okay, but in this line we have exact solution. Either this is true or not, or false. Okay.
Now we have distribution, so we can decide which, for example, if we are x equal to 5, we know that it is like 30%.
Yes, yes. For example, if we have this true or false value, we don't know what's the percentage of true values in the logic states. For example, this is maybe equal to the what? 55. But this false may be equal to 45. And so we cannot observe this probability rate or percentage rate in the what? In this logic state or in MLP application or the classification applications. But if we can convert this logic state into the probability, this may be observed from the what? From the users or by us. Okay?
Looks like normal classification without putting solution.
Yes. But in the probabilistic rate, we have averages. To what? We have averages. To what? To highest percentage rate, correct, or lowest percentage, correct. Okay, and so we can condition this area and we can classify the true rate in this case, and so we can decide the algorithm or the prediction is true or not based on this information. This is why we should or we transform every logic state or the absolute values into the probabilistic rate. Okay? For example, in the generative networks, we just only use the normal distribution to what? To classify or generate the new data. Okay? So, if this is the case, and then we need to create the R rules. For example, if we have this line in here, this is the normal distribution, but in every distribution, it seems like this is normal distribution, but your distribution may be different. For example, binomial distribution or the Poisson distribution. Yes. Yes, this is the normal distribution. But how can we interpret this rule, or how can we convert to the logic state into the probabilistic one? Firstly, if we have a decision about or the logic state about the 1 and 0, we should contain that. If the logic is 1 and the area interpretation is that or satisfy that the px dx is equal to the 1. Okay, because if we have all the chance for a given events, and so these events must provide this area, and so the collection of the integral of this area must be equal to the 100%. Okay? For any given data. Right? Do you understand that? Okay. In this case, if we have the 1 absolute values for a given state, if we convert this state into the probabilistic one, and so the happening chance to create this event must be equal to the 100%. Okay? But for different x values, we must contain every x values into the one probabilistic rate. Okay? And so this integral or the area integral of this probabilistic function must be equal to the 1. Yes. 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 Okay? But in the logic state or the MLP or logistic regression application, we don't have kind of feature. But in this case, we involve the chance or the probability rate, and so we may obtain the correct model or the happening models in here, like this one. Okay? And so, if this is the case, and then we should say that if there is a chance to create this event, we must say that Px at any x value must be greater than equal to the what? The 0. Okay? For x minus infinity to infinity. Okay? This must be provided.
Dx or integration of dx?
Yes. Or for example, this values 0.1. But this is not a usual case. The Px cannot be negative. Okay? There always be what? There always be a chance for a given x in this model. Okay? Otherwise, we cannot model because it's nonsense, right? Okay. So, this 2 form basically generates to the what? To logic state, to the what? Probability form. This is 1 dimension, this is 2 dimension, right? And so in the 2 dimension we can take a chance for the what? For an event to what? Provide happening rate or the occurrence rate or the chance to happening in this case. Okay?
And in 2 dimension we can use CAN for it.
Yes, but in this combination we have the semi-supervised learning or something like that. But in this case we can convert the whole the P or probabilistic rate or the parameters into the what? Into the neural network applications. Okay? Which call it the latent variable. In your latent. In Turkish, gizli, hidden space, latent space. Okay? So, this is the case, but in this case, we should create the what? The some parameters to model this normal distribution. Okay? Because in this case, we need to parameters in order to what? Model for a given data set, right? If you don't have any parameter or any scalable parameter in here, and then we don't have any model. Okay? So, how can we derive the generalized parameters in here? Firstly, we need to give the what? I'm sorry. Okay. So, how can we derive the generalized parameter in here? The problem is that can define the problem like this one. Assume that we have a data like this one. Just come here and sit down. We fix it. Okay. And so we have the n sampling number in here. And y is given at this stage. Okay? And so we have a distribution like this one. This is sinus signal. But in a probabilistic model, we need to give the what? The generalized coefficients or the parameters in order to represent the probability rate, because if we have some specific scale or constants in here, and then we can scale the our model, like the for example, if you have the linear regression model, and then we can offer that theta 0 plus theta 1 times x, right? And so these two parameters creates the model. But how come, or what is the parameters of the probabilistic models in here? So we need to say that the multiple straight lines can be used to model in here, like this one. For example, we have the one line, and one line, 3 line can be defined these parameters, or sinusoidal line can be used to define this signal. But in the probability, we need to generate some specific constants to model everything or every data, or we should find or search the generalized pattern, generalized coefficients to model any data. Okay? Because the sinusoidal data or sinusoidal model is fitting this one, but in the other case they could not be. Okay? So what we have in this problem, we have y or x data in here, like this one. We have the n and x values in here, because in each case or in every case we have this number n or x. Okay? For a given data we have, for example, 100 sampling number, and which is equal to the 1, 1.2, 5, 4, 100, 4. Okay? This is the representation or distribution of the data. Yes, we should drive everything from this one. Yes, but x, for example, 1, 2, 3, okay? The target values or your data set, okay? So, we need to define the generalized coefficients, which means that this is the expected values. Have you heard about that? Expected values? Expected values. What's the meaning of the expected value?
The value we predicted to match with output.
Yes, the expected value is the expected value. Okay? The most likely happening rate or the values of our data set. Okay? And so, how can we obtain this data set? This is the easiest way to find it to the if we show that we have a bias value in here, like this one. And so, most likely, this data could be generated at this line. For example, this is equal to the 3 or 4, okay? This data is around 4 values, or 5 values, or 100 values, or 200 values. This is highly to the most expected value. And so, how come or how can we calculate this value? No, the expected value can be defined with the if we collect the whole term like this one, xi, and if we divide to the n, and so we can have the expected values, which means that which is equal to the mu or mean value. This is the definition of the mean value. Mean value represents directly to the most expected value for a given data set. Okay? You understand what's the meaning of the mean? Average. And the average is the most expected value in your data set. And in every data set, in every different data set, it's the same way to calculate these distributions, right? This is the generalized pattern for for defining to the to your distributions. Okay? And so, how about the deviation rate, because this is the most expected value, but we have the what? Deviation values. How can we calculate this value? Yes, yes. And so in the second place we have another contribution in here, the variance, which means that if we have the expected value, we can calculate the expected value minus x, and so this gives us the deviations. Okay, and so if we take a square in here like this one, this is what the negative and positive converts to the what? The positive values, and if we divide to the n, we can say that that's the variance value. If we're taking the square root of this term, and so this is the standard deviations. Okay? These parameters is utilized to the what? To build your probability rate or probability function, because at every data set we have the x value, okay, data set value. Yes, we can model every data set, every different data set, every different kind of data set can be modeled by using these terms, without define to the what? Any specific model like this one, or like neural network, or like convolutional neural network, right? We generate the patterns, okay. And so if we have the mu value, if we have the variance, standard deviation, and px body, and so how can we create this area or probabilistic area? By using these terms, because this is what? The model parameters, right? Like theta 0, theta 1, blah blah blah.
We can use to build the distribution. And from the distribution we can build the model.
Yes, but this distribution must be built with the what? The expected value, variance value, standard deviation, because it's standardized whole the data into the one space, one probabilistic rate.
I mean that mean and standard deviation, it is not our weights of model. We will use it to build the weights.
Yes, but these values should be calculated from the what? Yes, in the generative networks, we change the mean, variance, and standard deviation of this probabilistic model, and then if we take or if we give the random signal to the neural network, yes, we can generate an image. This process in a reverse way in this case, right? You get it? Because the model is general, right? Okay. And so, how can we define this rate? Firstly, we need to give the what? This function. If we model these things, and so px must be evaluated for the what? Mu and variance. Okay? What's the meaning of this? Meaning of this is probability of x for a given mu and sigma values, or mean and variance values. Okay? This is the model parameter. And so, how can we equalize or create the area form to build to the what? Integral px dx is equal to the 1, which means that we should use the mu value, variance value in here, and then we should give the sum or define the sum function in here like this one, and then always this value must be greater than 0, and also whole the values or the summation of the whole values must be equal to the what? To 1. Okay? And so we should give the what? The exponential curve in here like this one, and so x mu square divided by 2 sigma, so that this is the, yes, Yes, and we should scale this function with the what? With this term. Square root 2 pi and variance value. What's the meaning of this? This function creates to the what? To this shape in a normal situations. Okay? Just like this one. And so if we have this notation like this one and the highly expected value which is given in the what? In this case, right? Which is mu. Because which is the most likely expected values. Okay? Yes, but this function is built by the what? Gauss. Okay? Gaussian distribution, the normal distribution. But this function must be built with what? The mu values or standard deviation values or the variance values. And so this probabilistic rate must be high at the what? At the mu values. Okay? And after that we have the mu plus standard deviations in here like this one. And so also we should give the what? Minus standard deviation, and then minus 2 standard deviation, and mu plus 2 standard deviation, and goes on this right. Okay? And so what about this term? This term only corrects to the what? The px dx is equal to the 1. This is provides to the what? This one. This is the scale factor to what? To select or generate the integral must be equal to the 1. Okay? Just like that. This term, for example, we can model this generation, this model by using only this exponential function. Okay? But this is a scale factor to the what? To provide the what? The integral of the probabilities must be equal to the 1. This satisfies these conditions for a given exponential function. Okay?
The integration of exponential equals to the inverse of this term, so do we get 1?
Yes. We just what? Scale this factor by using the what? The standard deviation and the pi values. What's the meaning of the pi? If the integral of the exponential term is given in here, and so we need to divide and or multiply with the pi values. Okay? So, you understand what I'm saying in here? We can... Yes. But it must be 1. Yes, this one creates these terms. And so, the integral of this term, for example, only for exponential integral, may be 4 or 5 or 6. But in this case, we must satisfy to what? This integral must be equal to 1. Okay? That's the whole condition to what? To generate the normal distribution in your applications. Okay? This is called to the what? The probability density function. Okay? Firstly, we just simplify the whole notation in here, like this one. For example, if we have the n data in here for n x values, and so if we have this model like this one, if we use the probability density function and then we can generate the probability rates of these terms like this one. For example, this is the pay x, and so this is the x, and then how about the mean or expected value like this one, right? And so we can generate to the what? The mu values in here. Okay, and so what about the standard deviation? Standard deviation gives us to the what? and then we can build the R model with the what, with these terms, like this one. Okay, and so we can write it down. This is the mu value in here, and so this is the what, mu plus sigma, and this is what, mu minus sigma. Okay, this is our generation model of this one. And so the outcome of these terms, for example 0.3, but in this case 0.05, 0.05. And so what is the output of this generation? Most likely we expect the 5 values, but this is the what, for 5 or 5, 5. Okay, and so the probability of probability of the outcomes is equal to the 4.5 is equal to the what, 0.05 values. Chance of, yes, yes, but most likely we have the expected values in here. Maybe we don't know, but maybe it's the highest probability of these terms.
We can say that for every change of 0.5, if it change 0.05 is our.
Yes, this is the model representation, but if we do to what, variable standard deviation, which the generative networks applies these things, or multiple probabilistic rate function, and then we can generate to the what, the each model in here, like this one. Okay, so in the classification problem, for example, if you have the what, these terms like this one, x2 and x1, and if you have the, for example, this the 4 and 3, and we may have this classification data in here, and so we have a class at this time. Okay, and so we can say that this probability distribution function right now is what, 2, right? 2 probability density function is given in here, because we have the x1 distribution and we have the x2 distribution, right? Okay, and so mu1 is equal to the what, 4, mu2 is equal to the 3, and so sigma 1 maybe 2.2, sigma 2 equal to 3.1. Okay, and so we have the P(x1) and P(2)(x) values in here, right? And P(1)(x1) and P(2)(x2) at the probability. Okay, no, so this is the x1 and x2. If you have the 2 data to input your network or the model, and so we can draw that. And if the 2 distribution is given in here, and then we can say that 2 probability function must be used in here.
We will make the good distribution and get the overlap between them, and this will be the class, I think.
Yes, but in the combination of this model, we should define the Gaussian mixture model.
Yeah, we will make the normal distribution for each probability.
Yes.
And the overlap between them will be the class.
Yes. For example, up this this example in here, like this one, we have the 1 probability distribution in here, P1, and 2 probability distribution, P2 in here. Okay, just like this one. And after that, maybe if we can, condition is that P1 x1 greater than 0.7 and P2 x2 greater than 0.7, and then we can say that this is the C1 class. Yes. 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 But the one, Yes, one class, one distribution is not enough to represent your data. In this case, two. Yes, two x1 and x2 must be utilized in this case, and so each x1 or x2 have to what? Probability distribution, and each function must have the mu values or the sigma values to represent this class or these class notations.
If we have one class property, we can do it by just two.
Yes, for example, if we have the something like that.
By just doing the probability equation.
Yeah, no. If we have the x1, and so we have the what? The one probability function. For example, in this case, we should give that.
We have defined another probability distribution.
Just like this one. Okay? We have two mu values, and in the next later we will call that components.
So it is not normal distribution.
This is normal distribution but with many components, which is called the Gaussian mixture model. Yes. Yes, we have the two mu values because if we may have this kind of data set like this one. For example, if we have the classification problem, this is the C1 and C2, and so we have the what? Two mu values, right?
For each class we have
Yes.
two values and it's a standard deviation.
Yes. For each class, we should get the what? The one standard deviation and one mu value to model it. Okay? In the next lesson, for example, we will talk about it. Okay. So